Good morning, everybody. Welcome back to the Dean's Coffee Club. It's been a few months since we've met, but hopefully people have been doing well and enjoying a little bit of winter weather off and on since the beginning of January. If we have some new people here, I'm John Newhook. I'm the Dean of Engineering. I've been the Dean of Engineering for about 3 years now. The Coffee Club is something we've been doing, I think, for about 10 years, with the idea of having a little more of an informal get-together, which is why we call it a coffee club, to update alumni and other interested people on some of the things that are happening in the faculty. And we normally have a faculty member or a key person in our faculty operations present an update. And we're very fortunate in this session to have Dr. Paul Amyotte come and talk about actually what he's doing now, but also a perspective that for the past 10 years, he's been the CD Howe Chair in process safety. So he's going to give us both a little bit of a retrospective of the chair and the work that's done, and certainly where we are right now and where he is in process safety. Before we begin, a couple things. One is we continue, of course, to adapt to COVID. I think this term, one of the things we changed to try to enhance the experience for the students was we have 9 courses, mostly in the senior course realm, where students who are in Halifax are able to come in and participate in the experimental lab portion of their course in person, and capstone projects. Some of the students are able to come in and do some of the building for their projects. So we thought that was an important improvement this term. For the students who can't be in Halifax, there is a virtual participation process where they can work with the students who are in Halifax. So that's been important for us. We're going to continue that through the summer, and then in the fall, we're hoping to actually do even more of it. So more courses, more students on campus being active as we continue to transition and adapt with both the national provincial response to the pandemic and the types of restrictions and permissions we have. I also want to point out that we've hired a new person within the faculty. Some of you may have met Craig Arthur in the past, who was the manager of facilities and safety. Craig has moved on to another position in the university, and we've just started this month Leanne Sandula. Leanne has joined us as our new manager of facilities and safety with the faculty, so that's great. Again, we are focused in delivering as high an online education as we can, and at the same time trying to expand the student experience with on-campus and other experiences as we can in this current environment, and continue research and other activities. I will hand it over in a second to Dr. Amyotte to give his presentation. For those of you who are participating before, you know the drill, but for anybody who's new, you can submit your questions in the question and answer section and submit them as they come to you during the presentation. I think Paul may even have his slides numbered, so if you want to reference a figure or something that was said on a particular slide, you can even type the slide number in your question. We'll compile those during his presentation, and then at the end, we'll have a process where I ask Paul some of the questions you submitted and he answers them. So that's how it'll work. Again, thank you all for joining us. It's an interesting environment, and I think we've had some good interaction in the past, and I look forward to it. And with that, Paul, I am happy to hand it over to you to give your presentation.
Thank you, John. I appreciate this opportunity very much. It's a welcome change in my normal routine, and very happy to be here. So thanks again, John. So I'm going to talk about our process safety research at Dalhousie, as John mentioned. It's obviously occurring in the current pandemic, and we're all living through this pandemic. And there'll be some discussion a little bit later about some of the research we're doing that is directly applicable to getting through this pandemic. So I'm going to, just by way of an outline of what I'll talk about in the next half hour or so, I'm going to define process safety, talk about our research at Dalhousie as a global endeavor. Then I'm going to briefly touch on three topics, three basic concepts that we'll need to get a bit of an understanding of as we go forward into the discussion of our research. And those concepts are dust explosions, inherent safety, and bow tie analysis. And then I'll spend some time on three current research projects we have on the go: marginally explosible dust, the use of bow tie analysis with combustible wood dust, and also I'll try and demonstrate the applicability of bow tie analysis to dealing with the current pandemic. And I'll conclude with some acknowledgements and final remarks. So what is process safety? Well, I've got a slide, but I'm going to first let the U.S. Chemical Safety Board describe what process safety is all about.
June 21st, 2019. The Philadelphia Energy Solutions Refinery in Philadelphia, Pennsylvania. At 4 a.m., flammable process fluid containing mostly propane, along with a small concentration of highly toxic hydrofluoric acid, or HF, escaped from the refinery's HF alkylation unit, likely through a ruptured pipe elbow. The alkylation unit produced components of high-octane gasoline. The leaking process fluid formed a large ground-hugging vapor cloud that surrounded some sections of the unit. 2 minutes later, the cloud ignited, causing a massive fire. A control room operator quickly took steps to prevent the release of additional HF by rapidly draining the unit's hydrofluoric acid to a special vessel designed to hold the acid in the event of an incident. At 4:15, during the ongoing fire, an explosion erupted in the alkylation unit. 4 minutes later, a second explosion occurred. At 4:22, a process vessel in the unit containing flammable hydrocarbons violently ruptured, causing the largest explosion. A large 38,000-pound fragment of the vessel flew across the Schuylkill River and landed on the river's opposite bank. 2 other fragments, one weighing about 23,000 pounds and the other about 15,500 pounds, landed inside the refinery. The fire burned for over 24 hours until it was finally extinguished the following day at about 8:30 a.m. 5 workers sustained minor injuries during the incident and response. The CSB is unaware of anyone experiencing health impacts from the hydrofluoric acid release.
That's what process safety, the principles of process safety, try to prevent. We'll just move on here. Just kind of hung up a little bit, but we'll get there. Oh, we don't want to watch that video again. There we go. So here's the slide on process safety. I thought the video would do a better job of explaining the type of incident that we try to prevent with our principles of process safety, but here's a few definitions. Chemical engineers are often thought of as process engineers, so I thought I'd first define a process. It's really just anything that we do in chemical engineering and process engineering that involves highly hazardous chemicals, and that's a lot of the operations that chemical engineers undertake. So what is process safety? Then it's the prevention and mitigation of process-related injuries and damage arising from, and these are the big 3 things we try to prevent: fire, explosion, and toxic release. So some people would call this perhaps system safety, and that's our focus. We try to prevent and mitigate loss to people, property, process, and environment. Property loss is, of course, equipment damage, asset loss. Process loss is business interruption. We also try to avoid loss of control of chemical processes and loss of containment of what's inside the pipes and vessels. So as you can see, process safety is very different from occupational safety, in which the focus is largely on protecting the individual and the avoidance of human injury. As I mentioned then, we talk about process safety being about keeping it in the pipes, and the it is the hazardous materials and the energy that they contain. When we don't keep it in the pipes, we end up with catastrophic incidents such as first Bhopal in 1984, release of methyl isocyanate, which killed thousands of people that night in 1984 in December and has caused untold suffering to this day. Mexico City, excuse me, in 1984, liquefied petroleum gas, an offshore oil and gas rig, Piper Alpha in the North Sea. Phillips 66, 1989, that was a polyethylene plant which suffered a vapor cloud explosion. I've included Westray here, not the process industries per se, but obviously a devastating incident in our own backyard, so to speak, in 1992, in which 26 miners were killed. Toulouse in France, an ammonium nitrate plant, BP Texas City, and so on. At a refinery, Buncefield and oil storage depot in the UK. BP Horizon, that's the Macondo well in the Gulf of Mexico. You'll remember that, the catastrophic, devastating environmental loss. But also at the time that that explosion occurred, 11 people were killed. Fukushima in Japan, we remember that, of course. You might wonder what's that doing on the slide. We can't, that I know of, prevent tsunamis, earthquakes, and hurricanes, but we have to be prepared to deal with the consequences of these natural occurring disasters on our nuclear power plants, oil refineries, and so on. Tianjin, a port in China, again, an ammonium nitrate explosion. And most recently, of course, you'll be familiar with what happened in the port of Beirut in Lebanon. Again, massive quantities of ammonium nitrate being stored inappropriately. Not a process incident again, but many, many warning signs from the process industries that could have helped to prevent this type of incident. So I just wanted to talk a little bit about what we tried to do over the past 10 years in taking our research globally and collaborating with people around the globe. Of course, here we are in Halifax with our team at Dalhousie and local people as well. My primary research colleague is Dr. Faisal Khan at Memorial University in St. John's, so put him up and his team of people there. Faisal happens to be in Winnipeg right now with family. And truth be told, the two of us have been trying to get down to Texas A&M to the Mary Kay O'Connor Process Safety Center for sabbatical, but unfortunately, I don't think that's going to happen. So we'll just, at least not for a while, we'll take that off the map for now. We are collaborating. One of the projects I'll talk about is with people in British Columbia in the wood pellet industry. The Marginally Explosible Dust project that I'll run through shortly involves the work of Albert Ado, who's a PhD candidate. Albert went home to visit family in Ghana for Christmas, and Albert's still in Ghana and likely will be there for some time, but that's all right. We're proceeding virtually, and his safety is first and foremost. Albert's collaborating with Dr. Ashok Dastadar in Chicago on some testing that I'll describe shortly. And we were very happy to have with us last year, for all of last year, Yaji Bu from Northeastern University in China. Yaji arrived in January of last year. A couple months later, went into lockdown with us, worked from his apartment in Halifax, and then returned to China this January to go back into quarantine and isolation. But a wonderful young man who we really enjoyed having with us. And along the way, on a daily basis, as editor of the Journal of Loss Prevention, I collaborate with colleagues in Europe and India. So when I look at this map, I just have to say to myself, it's indeed a small world. It's also a beautiful world. Okay, one of the things that, as John mentioned, holding the chair, it afforded me time away from teaching, a reduced teaching load. So I made a conscious decision to work on communication vehicles, to teach and educate in the process safety field for both undergraduate, graduate type education and also research. So we were successful in producing a number of books in that area. Also had the opportunity to work with various groups in the United States, in Canada, and the United Kingdom on different projects that were very, very interesting, and I think brought some degree of profile to Dalhousie University, and also greatly benefited from the work of the people in my research team. So the first basic concept I wanted to touch on before getting into the actual research projects is the dust explosion. So I'm sure you're familiar with the fire triangle. We need a fuel, an ignition source, and an oxidant to have a fire. The fuel in this case is a solid combustible material, a dust. We get to the explosion pentagon by adding two extra sides to this construct. The first is mixing. We need to get the dust up airborne and formed into a cloud. So we have mixing of the fuel and the oxidant, which is the oxygen in air. And then we have some degree of confinement around that cloud. So as combustion with ignition, combustion proceeds and the temperature rises, the pressure also rises because of the confinement. And then we have mechanical work done on the boundaries of that confinement, and that's giving us an explosion. You're probably familiar with coal dust and grain dust explosions. I mentioned West Ray. Coal dust explosions happen, unfortunately, throughout the world with alarming regularity. Grain elevator explosions as well. But there are many other materials that can lead to a dust explosion. For example, polyethylene, and these are pictures of incidents that have been investigated by the U.S. Chemical Safety Board over the years. Polyethylene, phenolic resin, aluminum, many metals, most metals are explosible. The bottom right-hand corner shows a picture of the devastation at the Imperial Sugar Refinery in just outside of Savannah, Georgia. Just a horrific incident in which there were a large number of fatalities and complete destruction of the process plant. So I want to show you just an example of a dust explosion. This is a piece of equipment that we have in our lab, purchased with the kind assistance of NSERC, Natural Sciences and Engineering Research Council of Canada. So you have a glass tube in which we're going to form a dust cloud. The dust will come from the base of the tube, being dispersed by an air blast. About a third of the way up the tube, you see the two spark electrodes across which will pass the spark to ignite the dust, and then the explosion will develop. So what you saw was the initial explosion. I should mention this is for nylon fibers, but then also lingering combustion in the cloud. And this gives us some insight into the horrific accidents that occur sometimes in textile mills where fibers burn and explode. The shock wave, the blast wave from the explosion, of course, does damage, but also significant harm to people occurs because of the flames that linger once the initial blast wave is passed. This is an example of nano-sized titanium. So it's a metal, and it's a very small size metal. A little bit of a different look at a dust explosion here. Now it's a little more dramatic than it needs to be. That's just a normal digital camera. There's no filters or anything, so it's a lot of light coming into the camera lens. But you can see that the burning and the explosion is quite different from what we saw with the nylon fibers. You can see in the glass screen there, the plexiglass screen, that's Ivan Yarossi, an exchange student from Turin in Italy. Wonderful young man, came and spent 6 months with us. Great researcher. It's amazing. He never flinched during taking the taking of that picture. All right, the other basic, or the second basic concept is inherent safety. This is a concept that was developed by Professor Trevor Kletz in response to what happened at Flixborough in 1974. About 40 tons of a chemical called cyclohexane, similar to gasoline, were released at this plant. It was a nylon intermediate plant. And as a result of this incident, a lot of people started thinking about adding on safety devices and developing procedures. Trevor asked, why do we rush to implement add-on safety devices and develop these procedural safety measures without first considering whether we really need these massive inventories of hazardous materials? He wrote a paper and he coined the phrase, what you don't have can't leak. So with inherent safety, we're talking about trying to remove hazards at their source. A couple of quick examples. Classic Kletzian examples. If we're concerned about the hazard of stairs in a 2-story house, we can add landings and handrails and tell people to be careful, or we can remove the hazard and live in a 1-story house. Easier said than done, but that's the basic principle. There's a strong life cycle approach to this concept as well. From a stability perspective, what's inherently safer than that antique-looking two-wheeler there? Of course, it would be a tricycle. So that's the essence of inherent safety. We place inherent safety in what we call the hierarchy of controls. When we're faced with a hazard, there's only 4 ways, general ways we can deal with it. Least effective, work with people, safe work procedures, and so on. Next up, in terms of effectiveness, we add on safety devices that require actuation and detection, sprinkler systems, for example. Then we add on safety devices that don't require actuation and detection. They will just work by their mere presence. So an explosion rupture disc, for example. Most effective inherent safety, eliminate hazards, minimize hazardous inventories, substitute with more benign materials, and so on. The third basic concept is called bow tie analysis, and this is a form of hazard identification and analysis. So we start with a hazard that will lead to a top event. This is something we don't want to happen. The top event will be caused by a threat, and usually there's many threats that will lead to that top event. There will be consequences arising from that unwanted event. But we can put barriers, prevention barriers, between the threats and the top event. These are our safety devices that act before the incident occurs. And we also put barriers between the top event and the consequences. These are called mitigation barriers to help deal with the severity of the consequences. We put it all together and it looks like a bow tie. I think it does. It's called bow tie analysis. Perhaps you'll agree. You have in the center, the knot there, the hazard and top event. You have essentially a fault tree on the left-hand side and an event tree on the right-hand side. You'll notice degradation factors and degradation controls. That's simply saying that each barrier, each safety device might fail. And how can we try and control those barrier failures? Okay, so the first project I wanted to talk briefly about, and these are things that we have ongoing right now, is on marginally explosible dusts, funded through NSERC, through a collaborative research and development grant with support from the chair and also my discovery grant. People involved at Dalhousie, myself and Albert Ado. There's Albert up in that picture, pre-pandemic, operating the 1 cubic meter chamber in which we've done some testing. Martin Cloutier, PhD student here in Halifax, also a consulting engineer. And you can see our partners located in the US and Canada, Professional Loss Control in Fredericton, New Brunswick, and also the key collaborators. So this project is all about a matter of scale. There's the Dalhousie 20-liter explosion chamber in which we have done thousands of tests over the years. We disperse the dust, we ignite it, we measure the pressure rise, and we determine explosion parameters and other things. So we can get about 4 tests done, 3 to 4 tests an hour. It's a very versatile, useful piece of equipment. But what we determine in this 20-liter chamber has to be applicable to industrial scale. So we check at the intermediate stage of a 1 cubic meter chamber, 50 times the volume, 50 times as much dust per test. You can't do as many tests per hour. You can get maybe 1 per hour done. There's Albert again, demonstrating that he can use that chamber. This chamber is the one that I mentioned with Dr. Ashok Dastadar at Fauske, just outside of Chicago. So what's the problem with this? Well, it's a dilemma for industry. So here we're testing 2 sizes, fine and coarse, of polyethylene powder. The 2 graphs on the left-hand side, top and bottom, are the explosion pressure, the overpressure, as a function of dust concentration. The 2 graphs on the right-hand side are the rate of pressure rise, how fast the explosion is proceeding as a function of dust concentration. The red line, the triangles, that's the 1 cubic meter chamber data. The black line, the circles, that's the 20-liter data. We'd like those 2 curves to match up very well, and they generally do, except down here for the coarse polyethylene with the rate of pressure rise. So which results should we use to design explosion prevention and mitigation measures? It really matters. It's expensive to bring in these measures, so we don't want to overprotect, but if we underprotect or say the dust doesn't explode, when in fact it will at industrial scale, we're obviously greatly increasing the risk. So there's a number of groups throughout the world, including ours, working on this. Current status for us is we've just completed some testing, again, with Albert in Ghana and Ashok in Chicago and me in Halifax. So we've got the data acquisition, and now we're analyzing carbon black, which we obtained from Michelin, oat grain, urea, and zinc. So that work is ongoing. The second project I wanted to talk about is a very recent one, using bow tie analysis with combustible wood dust. The funding agency here is WorkSafe BC, supported by the chair and my discovery grant again. People at Dalhousie are myself, Eric Brideau, a master's student. Eric's also a consulting engineer in Halifax. Kaylee Rayner-Brown, a research associate with me. Kaylee did her master's, finished last year, one of the first people to defend her master's degree during lockdown. Just doing an excellent job in facilitating these bow ties with our partners out west. And you can see Chris Cloney here in Halifax is one of the partners, as well as Wood Pellet Association and BC Forest Safety Council. So what are we doing here? Well, here's an example of a hammer mill. This is used in the wood pellet industry to take sawdust, wood chips, reduce their particle size to get them ready to be made into pellets. Here's the bow tie knot. The hazard is combustible wood dust in the hammer mill. The unwanted event, the top event, is a dust explosion. We have lots of threats, and I realize those are a little bit difficult to read, but they all relate to basically different types of ignition sources that could occur. We have lots of consequences, and they all relate to people being hurt, but in various ways, to business interruption, to asset damage, to harm to the environment. Oh my goodness, we put in a whole bunch of prevention barriers. That's getting busy. Let's get one you can see. So this is for the threat of an ignition source due to foreign debris, rocks, and tramp metal coming into the hammer mill with the feed stream. So we have a prevention barrier of mechanical scalping to separate rocks from fibers. The next barrier I want to show is for the threat of hot work, so bringing ignition sources, say for welding onto site. So here our barrier is use of fire extinguishers and fire hoses and equipment being maintained and so on. Those are procedural, active type barriers. They're not inherent safety yet. So then we go to mitigation barriers, degradation factor controls. The bow tie gets very, very busy because it's being done by people. Here's a picture of folks at one of the wood pellet facilities in BC pre-pandemic, brainstorming around the types of barriers and threats and consequences that we might see. So the current status of this work is I say, it's quite recent. So we're doing ongoing facilitation of the bow ties with the various units at wood pellet facilities. And what that is, process safety in a pandemic, that is me sitting in my house in Cole Harbour, Kaylee in her house in Halifax, facilitating. Kaylee's doing the facilitating with these folks sitting out in British Columbia at one of the wood pellet facilities. And they are sitting 6 feet apart, all masked up, hand sanitizers, well-ventilated room. It's quite an interesting procedure. So now we're working on incorporation of example-based guidance to get more inherent safety thinking into these barriers. We've also just submitted a follow-on research proposal to WorkSafe BC with our partners this time, Wood Pellet Association of Canada and the BC Forest Safety Council. So getting near the end, the final project that I wanted to talk about that we have ongoing is working with directly related to the pandemic and using bow tie analysis. So 2 projects, one last summer funded through the Nova Scotia COVID-19 Health Research Coalition. And we developed a number of bow ties looking at hazards and different receptor groups, threats and consequences for the novel coronavirus. And we were successful with that work, successful enough to then apply and receive an NSERC Alliance COVID-19 grant. This has also been supported by the CD Howe Chair. People working here, myself, Peter Van Berkel in industrial engineering at Dalhousie. Peter has been absolutely instrumental to this work with his knowledge of the healthcare industry and so on. And also, it's great to be working with an industrial engineer. Love chemical engineers, but it's not quite interdisciplinary, but it's getting there. Kaylee Rayner-Brown, of course, again, our research associate, and also Lauren Turner. This is her master's project. Lauren is a recent graduate of the undergraduate chemical engineering program. Also partnering with Faisal Khan at Memorial and Loudon, a PhD student there, our current partner on the alliance work, Nova Scotia Health Authority, with Gail Tomlin-Murphy and Tara Simpali. So I'm just going to cut right to one of the bow ties that we developed here. And you can see now that the hazard in the middle in the knot there is not wood dust. It is the coronavirus. The top event is that a resident, in this case, the receptor group is residents in long-term care facilities, that they might contract COVID-19. We've got some basic threats on the left-hand side and some unfortunate consequences on the right-hand side. So the threats are contact with the virus due to visitors, an infected resident, or an infected nurse or caregiver. So here's some barriers we can put in place for those three threats. We can close the long-term care facility to the public. Social distancing, everyone's familiar with that. Pre-shift screening. We'd like to think that social distancing is inherent safety because we're getting a separation distance, but it's really procedural because it relies on me and you not closing that 6-foot gap, and we make mistakes and sometimes we do it deliberately. Mitigation barriers, you can see here, we have things like quarantining or isolation, PPE, personal protective equipment worn by staff, hospitalization. So now we put in degradation factors and degradation factor controls, and my goodness, again, it's getting busy. So let's focus in on a caregiver coming into a long-term care facility. One of the barriers is that they will wear PPE, personal protective equipment. How can that barrier fail? There could be a shortage of PPE. How can we try and control that failure or degradation? Through a coordinated response to purchasing, through an expedited authorization process for personal protective equipment, for example. So these are all barriers, all things that we've experienced as we've lived through the pandemic. We've been trying to organize them in a coherent, cohesive manner with the use of bow tie analysis. So the complete picture, it's not the complete picture, right? We don't have all our barriers, we don't have all our degradation factors and so on. So the current status with this work is that we've had some recent meetings and ongoing discussion. In fact, we have a meeting this Friday with folks from IWK and Nova Scotia Health Authority. It's really exciting work for us because there's a good deal of enthusiasm from our partners. And we'll be looking at bringing true inherent safety considerations into this analysis. I have to say, former Premier McNeil and Dr. Strang, they were getting really close to inherent safety. Maybe they were even there with their state of blazes home, right? What a barrier, right? That's getting pretty close. We can't eliminate the virus just yet, maybe never, but state of blazes home is a lot of overtones of inherent safety. Really like that. And then we'll also be looking at exploring bow tie application it's a great communication tool. It can be used for policy making, decision making, and also post-pandemic operations. Well, that's a whirlwind tour. I hope I'm at about a half an hour, John. I just want to conclude by acknowledging a few people, my family. The chair position has given me funding and time. My family gives me love and understanding, and that's priceless. I want to thank all my research team members now, then, and in the future. Dean Josh Leon, under whom I started the chair, and of course, Dean John Newhook, who's been very supportive of my continued activities in the chair position. I want to acknowledge and thank the CD Howe Endowment Fund, NSERC, and all the other sponsors of our work. My final remarks. Okay, and I'm going to give some apologies to John Dunn here. No researcher is an island entire of itself. Every researcher is a piece of the university, a part of the global community. I truly believe those words. I want to say that holding the CD Howe Chair in Process Safety for that 10-year period and representing Dell in that capacity, it's been a real pleasure and also an honor. And I've been truly blessed to work with a lot of talented and dedicated individuals, especially those whose research I've presented today. Thanks, John. I'm happy to take any questions.
Thank you, Paul. You covered a lot of ground quickly. Impressive. I noted the global impact of what you're doing, and both in terms of your research team, but the projects and the issues you've been researching certainly have global reach as well. And I think that's something, as engineers, we highly value the impact we can make. And so thank you very much for that. First question I have for you, it's an interesting question from one of our viewers. Do you ever feel the pressure of having people's safety depending on your work? If yes, how do you manage that?
That's a great question. Um, I don't know if it's so much pressure as I feel a sense of obligation. You'll find that, and I have a lot of colleagues who do an awful lot of good work in this area throughout the world, in process safety, but also in occupational safety. I could name names of people, and they might be on this call, right? Of people I know, members of Engineers Nova Scotia, who just do such exceptional work in the field of occupational safety. I'm going to name a couple: Craig Arthur, Conrad Liliev. These are folks who are really out there working. I don't feel a pressure so much as an obligation, and it's not to sound highly noble about this, but I think you'll find the people I just mentioned and others who work in the field of safety do feel obligated to do a good job, to do the best they can, to do good in the case of a researcher, research that has really strong science and engineering underpinning to it, and then to communicate that in an effective manner. Because the classic, you have an idea, if you don't communicate it, you don't have an idea. So it's not so much pressure as a joyful obligation, I'll put it, to spread the story. Yeah.
Well, good. If I can follow up on that one. What has your experience been? I mean, you mentioned a project where you're working with a company out in BC, and I'm sure most of your other ones you're working directly with companies in one way or another.
Yeah.
What's your experience in sort of the industry perspective and uptake? This is something that have you seen changes, I guess, in industry's attitude towards safety over the course of your research career, not just the chair?
Yeah. Yeah. That's a great question too, John. I would say most of the companies that I tend to work with, because they're interested in our research, they'll partner through, and NSERC has some great, as you know, research partnership programs. They'll partner with us. They're already sort of there, right? They have a good safety culture. They're doing things, and they just want to improve. I have to be honest, I haven't really worked with a lot of companies that kind of don't get it.
Right.
They end up usually being the subject of an investigation by the U.S. Chemical Safety Board. And my colleagues in industry will say, what motivates them to do things well in this world is they don't want to be the subject of a CSB investigation.
Right.
What I have noticed is more opportunities, like with NSERC, and with other companies to partner in research, because they recognize that process safety used to be just kind of do your best, get out and work well in industry, but it's really becoming, it's not a discipline, but it's recognized as a key area of chemical engineering now for both practice and research. So I don't know if I've really answered the question, John. I think the companies I've worked with, they've always been there with respect to process safety, but they are improving. The unfortunate thing is that we continue to have these catastrophic incidents throughout the world. And you mentioned Beirut, that was not a process industry example, but massive quantities of ammonium nitrate being stored inappropriately. We need to bring the principles of process safety into these other application areas, and that's one of the things we're trying to do.
Good. Our next question is actually about the bow tie model method. Mm-hmm. Is the bow tie model commonly used outside of engineering? You mentioned it could be applied to public policy and public health.
Yeah.
But is it currently being implemented in other places, or is it mostly just used within the engineering field?
I would say mostly within the engineering field, but it's starting to get more diverse applications. It's, as I mentioned, it's a combination of a fault tree and an event tree. And if people know sort of those, they'll know that they originated, particularly fault trees. They've been around 40, 50 years. Started in the nuclear industry, aerospace. They found their way into some major multinationals in the oil and gas industry around the world. They've been using fault trees and bow ties for a while, so it has a strong presence in the engineering world. I've seen it used though, again, an engineering application for water quality. I remember being at a conference in the UK a couple of years ago, and a fellow was presenting on bow tie analysis in water treatment plants and such. It is. We did a literature survey, of course, in the healthcare field, and we're continuing to do that. There is some evidence of application of bow tie analysis in the healthcare field, not so much with the current pandemic, but in other applications. And I would have to say that probably what our healthcare partners in that work are most interested in, well, it's the logical presentation of cause and effect, but also the communication and potential for decision making that they're seeing. So long answer, short answer is primarily an engineering tool, but we think there's just applications everywhere. And I'll tell you, when we first went into lockdown last March, I started looking at the barriers that were coming in, social distancing, plexiglass shields, and I, in my own mind, started thinking bow tie, bow tie, bow tie. And then, of course, you think, well, if I can think of that, it's probably not a good idea. but then others started talking about it, so like, okay, it has applications elsewhere. Yeah.
Do you own a bow tie, by the way? No.
I do. Actually, John, I do, and I was going to wear it today.
Yeah.
But when my lecture a couple of weeks ago in our process safety course for chemical engineering students, we were doing bow tie analysis, and I did wear my bow tie for that lecture. So.
Good. I was very interested because I noticed you talked about an example with wood fiber, and we could argue that wood is one of the oldest materials that humans used for tools and fires and many other things, throughout evolution. So it's a very old material in that respect. And then you also mentioned some of the modern polymers and carbon and things like that. The issues with particularly around the dust explosions and the safety there, are there new challenges coming as we come out with new materials, or, is this becoming a bigger and more important issue because as we innovate and have new materials and new processes and additive manufacturing where we're using powder metallurgy and 3D printing with all kinds of different materials, is this making the problem more challenging or more diverse? Because, like I say, one of the projects you talked about was still a very old traditional material, maybe used in a slightly different way, but.
Yeah, it's all of what you just said. We started our own work in the dust explosion field. My PhD, and shortly after with coal dust. Now everyone knows, we've known coal dust explodes since the 1850s with Michael Faraday, but there always seemed to be more to kind of learn. And just when you think that you've got one material sort of sorted out, more things come up in terms of its application. More new things come along. You mentioned 3D printing, additive manufacturing, powder metallurgy. Yeah, there's all these new applications that come out. And any time that a material is generated, in micron size, you really have to start thinking about the potential dust explosion hazard. So these sort of older materials like wood and coal and grain, they've been studied a lot, and those incidents continue to happen. And it's not because we don't have the tools available, we don't have the knowledge, it's that we're not always applying them as we should. But there are these new things that come along and represent, oh my goodness, we didn't see that coming, and that we need to be aware of. So I'd like to think that the dust explosion problem will be solved someday, but it's going to be not in my lifetime.
And I guess one last question, Paul, before we wrap up today. When we look at one of the other new innovations that's coming, well, not coming, it's here, electric vehicles and other electric devices that have a lot of battery storage requirements, and batteries do catch fire and, and have issues. Just curious if you've had the opportunity to work and maybe even apply the bow tie model to sort of a situation like that, the kind of electric, and let's just say with vehicles for now, the electric vehicle industry and growth, and would the bow tie analysis be useful in that context of batteries and managing batteries against their own inherent safety issues?
I think you might have just given me a new idea to pursue, John. I hadn't thought of bow tie analysis with electric cars, lithium-ion batteries, and that. I have thought for a couple of years now of and I've had conversation here and there with Jeff Dunn, of course, our resident expert, world expert at Dalhousie on lithium-ion battery safety. And what I'm seeing as editor of the Journal of Loss Prevention is more and more papers being submitted on battery safety. Mm-hmm. And process safety doesn't quite capture that, but we're trying to look at expanding the scope so that we can deal with that from a technical journal perspective. But I would say, just off the top of my head, yeah, that's a great suggestion and something that I'm gonna look at. Thank you. Always looking for new ideas. If there's anybody on the presentation who wants to drop me an email with any thoughts or ideas, I'd love to hear from them. paul.amyotte@dal.ca.
And I know I said that was the last question, but we have one more, and it's about students, so I will ask it.
Yes.
What is your favorite aspect of process safety when you're teaching students?
Oh, when I'm teaching them, they get it. I mean, they get it, it's particularly with our co-op program, John, in the faculty. I'm teaching, like right now, I have 70 students in the process safety class, and I realized I'd never taught them before. I'd never, I'd never seen them unless I just passed them all, because I had missed this cohort entirely. So I said I want to talk to each one of you in a little Teams meeting, 5 minutes. And one of the things that I've been doing, we're with 50 of the 70 students so far. One of the things I've been asking them is, what experience do you have with safety? And a lot of them have really good process safety experience on co-op work terms. So they get it. And the others who don't, they've worked in retail, they've worked in fast food, they know about safety. The importance of the topic to them is not in question. And I find they're really thirsty for, I say the course that we teach will do one of three things, at different times. It's going to teach them something entirely new. It's going to give them the technical underpinning for something they've seen in industry, or it's just going to affirm something that they've already done, right? Like loco-tago procedures, hot work permitting, things like that, explosion relief fence and things. So yeah, that's a long answer. I think it's the fact that the students are very receptive. On the research side, I absolutely love working with my research team. Just a great bunch of people who come from different backgrounds and around the world. I mentioned Yaji Bu, the PhD exchange student from China. He comes to us, and 2 months later, boom, into lockdown. But the smile never left his face. I had actually met him in China a couple of years previously, and he just did tremendous work. So very, very talented people that I've been fortunate to work with, John.
Excellent. And I guess in closing, and thanking you for taking the time to have this presentation and discuss with us, I think we've got very amazing people at the university, and I know the coffee club is always a pleasure for me because I get a chance to just sort of pause for a few moments and listen to people like yourself discuss their research in more detail, and it's helpful for me, and I'm sure for any of the audience who has listened in. We do record these, so if there's somebody who missed this, this is available through our YouTube, I guess, so people who were unable to attend today can watch it. Thank you to everybody for attending this event. The virtual world has created some challenges, so we certainly appreciate people interacting with us in this different way. This is National Engineering Month, of course, so I would also encourage you to check out all the events that are happening. Engineers Nova Scotia would have a list of some of those, as well as other things that are going on nationally, and participate in those as you can. We don't have our next coffee club scheduled just yet, but we're hoping to have another one before next fall. But I think we'll probably have one more this year at some point, and then wait to the fall. And hopefully in the fall, we might even be talking about, can part of it be in person? And then we look at how we can combine sort of the value of having it recorded and available online for people who can't be in Halifax, but we are also anxious to, within the right safety parameters, to get back to seeing people face to face and interacting that way. So hopefully at some point in the not too distant future, which means some point where the year is still 2021, we can have more of a in-person interaction with our participants. But thank you again, Paul. Thank you to everybody. Have a great day, and enjoy National Engineering Month. Thank you.